All right, so 2.2 is called limits and continuity. We've already been dealing with continuity and discontinuities, but we are going to introduce a new topic today, or a new concept called the limit. And the limit is going to help us define the types of discontinuities that we've been seeing. We know how to identify what the discontinuities are, but we haven't really defined what they are. So the idea of a limit is going to help us do that. So first and foremost, as I mentioned yesterday, the limit is a y value, okay? But it is a y value that we are approaching, okay, approaching. So you could think of the limit as a notion of motion. It's movement, okay? Notice that it's different from a function value. A function value is also a y value, but it's not a y value you're approaching. It's a y value that you are actually at. You are standing at the coordinate 1, 3. Your y value is 3, and there you are. Whereas the limit, we're going to be hopping on the graph and moving closer and closer towards a particular x value and looking to see what the y value is that we're approaching. Okay? So the key word for a limit is the word approaches. Approaches. We're moving on the graph. You can think of the graph as being like roads on which you are driving, and you're looking to see as you're on the road driving towards a particular x value, what y value are you approaching? So we're going to do this real intuitively here on example 1. It says, for the function below, analyze what is happening to the y values as x approaches 3, x equals 3, from both sides of x equals 3. Okay, so I drew a little piece of a function there, called it f of x. The x location that I have marked here is 3, and here's what we want to do. Pick a different flavor here. If I hopped on the graph on the left-hand side of 3 and started heading back towards 3 from the left-hand side, as I get closer and closer and closer to x equals 3, my y value is getting closer and closer and closer to that solid dot, right? That's pretty obvious. We're getting closer and closer to that dot. So we're approaching 5. That's what we'll say. We'll say as x approaches x equals 3 from the left side. From the left side of x equals 3, comma, the y values are approaching 5. Y equals 5. Okay? And we're approaching 5 from above, but that's not as important. Okay? We're approaching 3 from the left-hand side, and as we get closer and closer and closer to 3, the y value is getting closer and closer and closer to 5. So like at 2.99999, we probably have like 5.00001. And if we get closer, like 2.9999999, it's going to be like 5.00001, right? Now what happens on the other side? Well, let's approach 3 from the right-hand side. Hop on the graph and start cruising along the graph like a road and start heading towards 3 from the right-hand side. Well, once again, you can see that as we get closer and closer and closer to 3 from the right-hand side of 3, your y values are again getting closer and closer and closer to 5. So let's go ahead and write that. As x approaches x equals 3 from the right side, comma, y is approaching, I was going to say y equals 5, or the function values are approaching y equals 5 again. Now that is a lot of words to write, isn't it? It's a lot of words. You think there's a shorter way to say that mathematically? Yes, okay? So this is the idea of the limit. Instead of saying this, what we're going to say then is the limit as x approaches 3 from the left is 5. In other words, 5 is the limiting value. As we get closer and closer to 3 from the left, the y values are getting smaller and smaller and smaller. They're decreasing, but they're not decreasing to negative infinity. They're decreasing approaching 5. So 5 would be the limit. So here's what we would write it. We would write it like this. We could say all of this stuff right here in pink, we can say it equivalently like this. L-I-M. L-I-M is lim. It's short for the word limit. And then underneath there, we put X, arrow, 3. Guess what the arrow means? Approaching. Now, because we're approaching it from the left side of 3, we're going to put like a little negative ionic charge, kind of where the exponent would be. That means from the negative side of 3. And on the horizontal number line, the negative side of a number is the left side of the number. And then we're going to go ahead and define the function, which is f of x. And then we're going to go ahead and say equals 5. So what we say right here in purple is exactly the same thing we say in pink up above. But notice the math sentence is a lot shorter than the English sentence. Here's officially how you would read this. The limit as x approaches 3 from the left-hand side of 3 of the function f of x is 5. Okay, that's just a fancy way to say as we get closer to 3 from the left, the y values get closer to 5. And similarly, what we'll say over here is the limit, LIM, as x approaches 3, the arrow means approaches. How do you think we're going to show from the right-hand side of 3? A little plus ionic charge looking thing, right? Because on a horizontal number line, positive numbers are found to the right. Bigger numbers are found to the right. Of f of x equals 5. Okay? So again, the pink words mean the exact same thing as the purple math symbols. We read this officially as the limit as x approaches 3 from the right-hand side of 3 of the function f of x is 5. Sweet. Now notice what is different about the function value. If I asked you for f of 3, how would you find f of 3? Or what is f of 3? Don't think too hard. It's the same thing. It's 5. Very good. But the way that we evaluate that is we don't hop on the graph and start approaching 3. If I ask you what is f of 5, you go to x equals 3, that vertical line. And you look up and you look down and you look up and you look down and you're looking for a piece of the graph. The piece of the graph is right there. It's the dot. Okay? So it happens to be the same. But it's not always the same. The limit from the left here happens to equal the function value, which is equal to the limit from the right. So notice the similarities. We define our function when we do function notation as f. We do the same thing here with the limit. The only difference is we define our input a little bit differently. In function notations, we put the input right there inside. We call it f of 3. For limits, we write the limit of f as x approaches 3. We put our independent variable underneath, behind the arrow, and we leave this as just generic f of x. Okay? Anything earth-shattering about that except for the new notation? Okay, well, let's try the next one, example 2. For the function below, analyze what's happening to the y values as x approaches -4 from both sides. Okay, well, if you look at x equals -4 here, you can see there's an obvious discontinuity, right? What type of discontinuity is that? There's a hole, okay? You would say that this function f has a hole at -4, comma what? 2, right? What is f of -4? Nope. 3, right? Because remember, when I say f of -4, that means you're going to x equals -4, and you're looking where the graph is defined. You're looking for the dot. The dot's right here at 3. So f of -4 is equal to 3. We could say that the function has a hole at -4 too, but we can't say that f of -4 is 2. But here's what we can say. We could say the limit as x approaches -4 from the left-hand side on the graph of f of x equals. Well, here's how you would evaluate it. You hop on the graph to the left of -4, and you start driving back towards -4. And now, as you get closer and closer and closer to -4 from the left, The y values are getting closer and closer and closer to the y value of the open circle, right? Which happens to be at 2. And similarly on the other side, you would say the limit as x approaches -4 from the right-hand side of f of x is something. You would hop on the graph to the right and start heading back towards -4. And as you do that, as you get closer and closer and closer to -4 from the right, once again, your y values are getting closer and closer and closer to the y values of the open circle, which still happens to be at 2. Now notice in the first one, the function was continuous there. The limit, as we say, from the left was 5, the limit from the right was 5, and the function value happened to also be 5. They were all three the same, and the function was continuous. That's not the same down here, right? The limit from the left is 2, the limit from the right is 2, but the function value is 3. So the limits give us a nice way to talk about the behavior of a function where it doesn't exist, in the neighborhood of where it exists. So you can think of the limits that we're evaluating, they're kind of analogous to being the roads, which is going to be the graph itself, leading up to an x value. Whereas the function value, you could say it's kind of analogous to, instead of a manhole cover, I'm going to call it a bridge. All right? Let's say that your goal is to drive across, and there's a canyon right there where that open circle is. You have a road that leads up to the edge of the canyon from the left, and you have a road that leads up to the edge of the canyon on the right-hand side. And the roads are kind of lined up with each other. But the bridge is way up here at y equals 3. You're not going to be able to cross there. There's a discontinuity. Now, if that bridge was built right there at -4, 2, you would be able to drive across perfectly. So the bridge would be the function value at that point, and now the limits are the roads, okay, leading in. You can think about it that way. And they're not the same, okay? So we're going to be able to define now what actually constitutes a removable point discontinuity, or a hole, right? We know how to find it from an equation. Plugging in gives you 0 over 0. But now we could say when the limit from the left equals the limit from the right, they're both 2 in this case, but that is not the same as the function value. Either the function value is a different number like 3, or the function value doesn't exist. You're always going to have a hole. When the limit from the left equals the limit from the right, the roads are pointing at each other, but if the function value doesn't exist or is some other y value, it's going to be a hole every time. Okay? Let's look at example 3. Kind of the same thing. Analyze what's happening to the values as x approaches 1 from both sides of 1. Well, we're not going to write the words again. We're going to use the notation. What would the limit be as x approaches 1 from the left-hand side of f of x? Anyone? I've showed you how to do it twice. What would be the limit as x goes to 1 from the left on the graph of f of x? Well, let's do it together again. Yeah, it's -3. Here's x equals 1. It's this vertical location. So you hop on the graph just to the left, and you start approaching it from the left. And as you do, you're getting closer and closer and closer to that solid dot, which happens to be at -3. What would be the limit as x approaches 1 from the right-hand side of f of x? Well, hop on the graph just to the right of 1 and start heading back towards 1, and you're getting closer and closer and closer to the open circle, whose y value is at what? -5. Okay? Now, just for comparison, what is f of -1, or f of 1, sorry? F of 1 is -3. Good. It just so happens now that the left-sided limit happens to be the same as the function value, because that's where the solid dot is. But the left-sided limit and the right-sided limit are, for the first time, different numbers. Guess what type of discontinuity we'll always have when the two one-sided limits are different numbers? Always a jump. So we have a way to define a jump discontinuity now. If the limit from the left does not equal the limit from the right, who cares what the function value is doing? It could plug one of those open circles or be somewhere else or not even be there at all. When the two one-sided limits are different numbers, we're going to have a jump discontinuity. So the limits of the roads and the function value is the dot, the bridge. Okay? Anyway, this kind of defines what we've just been doing, the first two bullet points. The limit from the left at any x value, call it c, is defined to be this. And again, we read that as the limit as x goes to c from the left of f of x. Similarly, the limit from the right-hand side of an x value c is this, little plus sign. Now I'm going to show you something, the general limit. There is something known as the general limit. And here's the theorem. It says if and only if in the middle. What that means is that it's a postulate. It works both ways. So you could start by saying if on this side, if the limit as x goes to c. What do you notice about this one right here from what we've been doing? Is that from the right or from the left? Does it say? No. So we call this the general limit. If there's not like a little plus or a minus sign saying from left to right, we call this the general limit. So here's what the theorem says. If the general limit is equal to some y value L, then the limit from the left is equal to L, and the limit from the right is equal to L. But because it's an if and only if, you can actually flip it around. You can start with this. If the limit from the left equals a finite y value L, which happens to equal the limit from the right, then we say the general limit without the plus or minus is L. Okay? So let's come back up here on example 1. The limit from the left was 5. The limit from the right was 5. Those are the same numbers. So here's what we could say by that theorem. We can now say that the general limit as x goes to 3 without the plus or minus of f of x equals 5. Okay? And then similarly, if we work the other way around, if I had just told you that the limit as x goes to 3 of the function was 5, you would then say, oh, so it must be approaching 5 from both the left and the right. It's an if and only if statement. The next one, the limit from the left was 2. The limit from the right was 2. 2 equals 2. So we can also say the general limit is 2. The limit as x approaches -4 without the plus or minus was also equal to 2. And again, working backwards, if I had just told you that the general limit was 2, you would be like, oh, it must be approaching 2 from both sides. The two roads are coming in and they're pointing at each other. Now, on the third one that we did for the jump discontinuity, the limit from the left was -3, the limit from the right was -5. Does -3 equal -5? No. So by the theorem now, we would have to say the limit as x goes to 1 without the plus or minus of f of x equals, and we'd have to write dne. What does dne stand for? Does not exist. By the theorem, the only time the general limit, which is without the plus or minus, is going to exist is if it's the same from both sides. So, if the function is continuous, will the general limit exist? If the function is continuous at a point, will the general limit exist? Yes. If there's a hole at an x value, will the general limit exist? Yes. Okay? If there is a jump at that discontinuity, will the general limit exist? No. Now, what about a vertical asymptote? We haven't seen that yet. Do you think the general limit is going to exist at a vertical asymptote? No, because even if it went up on both sides, let's say you have a vertical asymptote, and let's say that this is at x equals 2. If it went up on both sides, that means the y values are going to infinity, and if it went up on the other side, the y values are going also to infinity. Infinity, first of all, is not a number, okay? The limit from the left would be infinity. But when you tell me the limit from the left is infinity, you're telling me, number one, the limit doesn't exist because it increases without bound. So you're telling me two pieces of information. The limit doesn't exist. There's no limit to how high it's going to go because it increases without bound. The general limit would not exist here then, okay, because neither limit on either side exists. Okay, let's go ahead and look at example 4. This is kind of reinforcing now what we just did. When the two one-sided limits exist and are the same, and again what that means is the general limit exists, the function has either a removable point discontinuity at that x value or it's continuous, okay? When the general limit exists, it's going to have either a hole at x equals c, or it's going to look like this. The function would then also be continuous, or possibly. Those are the only two times the general limit will exist at a particular x value. The roads have to be lining up with each other for the general limit to exist. They can be connected by an open circle, that's fine, or they can be connected by a solid dot, that's fine. In both cases, the general limit exists, all right? Now, if the function value happens to equal the same thing as the limits, then it's continuous. But if the function value doesn't exist, or it equals something that's not the same value, then there's going to be a hole. So that's what we're doing on this example. I'm giving you a graph, and this is part of what y'all's group quiz tomorrow is going to look like, and part of what your test will look like on Thursday. I'm giving you a graph now. This is the function f of x. There's its name. We're going to evaluate these limits. But I'm going to let you do it, okay? Take about a minute or so and evaluate the limit from the left of 0, the limit from the right of 0, and then use your information from those two to make some kind of claim about the general limit. And if you finish that one, go ahead and jump to the next one. 1 minute. And you're trying this at home if you're watching the video. Don't overthink this. This should be an easy idea. The limits of the roads. The function value is the bridge, the dot. All right, that's a minute. Let's see how you did. The limit as x approaches 0 from the left. That's how we read that. The limit as x approaches 0 from the left. So you find x equals 0, which is also known as the y-axis, and you hop on the graph to the left. Now, you don't hop on the graph way to the left like over here, right? That's way too far to the left. You're approaching 0 from the left, so hop on the graph just to the left, like somewhere in here. And now, approach 0 from the left-hand side of 0. As you do, you're getting closer and closer to that red dot, which is at y equals what? 1. That's the limit from the left. The limit from the right-hand side of 0. Okay, hop on the graph just to the right of 0. Start heading back towards 0. And again, you're getting closer and closer to the red dot, whose y value is at 1. So the limit from the left is 1. The limit from the right is 1. What can we say then about the general limit at 0? It's also 1. Okay, the general limit exists. Now, of course, we can also say here that f of 0 is equal to what? 1. That's the red dot. Okay, that's the red dot, which I'll now make purple. So this function is continuous. If there was a canyon right there at the point 0, 1, we now can successfully drive across it. We have a road coming in from the left that's connected to the bridge, which is the dot, the function value, which is connected to the road on the other side, the limit from the right. They're all three the same y value, so the graph is continuous there. All right, take about 12 seconds and do the next one. 12 seconds, a random amount of time. If you haven't done it already. I'll give you a bonus 10 seconds. All right, let's look at it. Now, this is the limit as x approaches 3 from the what side? Left of f of x. So we find x equals 3, which is right here. Okay, or maybe I'll just highlight it vertically. So now I'm approaching 3 from the left. I hop on the graph just to the left, and I start heading back towards 3. I'm getting closer and closer to the open circle, whose y value is what? 0. So the limit from the left is 0. The limit from the right of x equals 3. Hop on the graph to the right, start heading back towards 3. As you get closer and closer to 3 from the left, you're getting closer and closer to the open circle, whose y value is still at 0. So if the limit from the left is 0 and the limit from the right is 0, the general limit then is 0. Notice the general limit, or the limits themselves, either side, they don't care about the function value. They don't care if it's an open circle or a solid dot. They're just the roads. So the general limit does equal 0. Now what is f of 3? -1. Yeah. The bridge, actually at x equals 3, was built way over here in the middle of nowhere. You can't drive across safely. You have a road coming into the edge of the canyon, a road coming into the edge of the canyon, and the bridge is like built way over here. That's a really crazy contractor. Someone was not communicating if the goal was to have the bridge connect the two. All right? So that is -1. So the reason we call it a removable point discontinuity is because all we have to do is relocate the bridge to 3, 0, and now the graph is continuous. That's why we call it a removable point discontinuity. So the limit gives us a way to basically define the types of discontinuities. And how do we define this one? When the limit from the left equals the limit from the right, and either the function value doesn't exist, or it exists and is at a different place, then you're going to have a hole at that point. The y value of the limit is the y value of the hole. All right, part B. If the two one-sided limits both exist, they're both finite y values, but they're different. As we already saw, you have a non-removable jump discontinuity. So go ahead and evaluate this one. The limit as x goes to -2 from the left, the limit as x goes to -2 from the right, and then based upon those two, say something about the general limit at -2. I'll give you 30 seconds. -1 DNA, good. Yep, good. Yep. Good. It's a new concept, but it's not a difficult concept. You just have a little bit different notation to learn. What's that? Well, you're approaching -2. So remember, if you're approaching it from left and right, you have to hop on the graph just to the left or just to the right until you get closer and closer to your desired x value. So yeah, if the solid dot is at x equals 0 and you're trying to get to -2, you keep going. All right, let's take a look at -2 from the left. So first thing you want to do is find -2 vertically. There's -2. If we're approaching from the left, you hop on the graph immediately to the left of -2, which I'll say is about right here. And then you start heading back towards -2. And as you get closer and closer to x equals -2 from the left on the graph, you're getting closer and closer to the solid dot, which happens to be at 2. But that could easily have been an open circle. Again, the limit doesn't care if it's a solid dot or an open circle. the limit from the right-hand side of negative 2. Now, again, you don't want to hop on way over here. If negative 2 is your destination, hop on right about here, just immediately to the right, and start heading back towards it. As you get closer and closer to negative 2 from the right-hand side, you're approaching the open circle, whose y value happens to be at negative 1. So the two one-sided limits exist, but those are different numbers, right? So what must be said then about the general limit? It does not exist. Very good. So anytime you have the two one-sided limits existing but not being the same number, you're always going to have a jump discontinuity at x equals that value. It doesn't matter if the function is defined there or not. Okay? They could plug one of the holes, be somewhere else, or not even be there. The limit doesn't care about the function values, ever. The function value is the bridge. The limits are the roads. Okay, so we've already talked a little bit about the vertical asymptote. We've just defined a removable point discontinuity by way of limits. We just defined a jump discontinuity by way of limits. Here is the other discontinuity, the vertical asymptote by way of limits. It says if you're approaching a specific value of x, call it c. C could be like a 3 or a negative 5 or anything. If you're approaching from the left and your y values are approaching infinity or negative infinity, okay, and or you're approaching that same x value from the right-hand side and your y values are approaching infinity or negative infinity. There's 4 possible things that can happen right there. You only need one of them to happen. If any one of those 4 things can happen, then there's a vertical asymptote at x equals that value. Okay? So let me go ahead and show you kind of a little example here. I'll just draw this little graph. We'll say this is negative 1. We'll say this is 2. And let's just draw a graph. Now, vertical asymptotes, remember, we designate with a dotted or a dashed line, but it's not part of the graph. Let's say I have this going like that. And let's say I have it doing this. And then we'll do that. Okay, so let's call this function f of x. So I just made this up. It's easier to draw a graph than it is to make up an equation for a graph. Because all you have to do to draw a graph correctly is make sure it passes the vertical line test. So let's go ahead and answer these questions off here to the side. Number 1, what is the limit as x approaches negative 1 from the left of f? What is the limit as x approaches negative 1 from the right of f? And what is the general limit as x approaches negative 1 of f of x? Answer those questions. And then when you're done, we're going to do the same thing at 2. All right, there you go. I'll give you about a minute or so to, well, 2 minutes. Let's do 2 minutes. Probably have to draw it and write all that out. So it's kind of the same thing we did for the other 2. Just have to write it in there. Pay very special attention to the notation because I'm going to hold you accountable for the new notation. The x arrow number goes directly underneath the limit, okay? And then your function kind of goes off to the right in front of both of them. You write the x arrow number directly below the limit. And your input is always behind the arrow, and then the function is always f of x or g of x. You never plug in the specific x value there. So you would never say the limit as x goes to negative 1 from the left of f of negative 1. Or the limit of f of negative 1. You define the input below with the arrow. All right, let's take a look at these then. So I made up that little function, and the first one says, what's the limit as we approach negative 1 from the left? So you look for -1, and you're analyzing the graph at that vertical location, okay? So as you hop on the graph to the left and you start heading back towards -1, your y values are going up, 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 up forever, okay? So the preferred answer here would be infinity. But as I already mentioned, when you say that the limit from the left is infinity, you're saying that the limit, first and foremost, does not exist. Because infinity is not a limit, right? If someone says you have unlimited potential, then your potential is infinite, right? There's no limit to what you could do. But you're also telling me then that the limit doesn't exist because the y values are increasing without bound. So infinity is the preferred answer, but guess what else is another answer that is technically correct? No, not negative infinity. The y values definitely from the left-hand side are going up, 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 up. You could also say on a free response, DNE, which means what? Doesn't exist, right? There is no limit. This goes up forever and ever and ever and ever and ever. Infinity is a preferred answer, and if this were a multiple choice question, I wouldn't have DNE as an answer choice. I would have like infinity or negative infinity, because it's a better answer. It tells you why it doesn't exist. All right, the limit as x goes to -1 from the right-hand side is what? Hop on the graph to the right of -1, start heading back towards -1, and guess what? You're doing the exact same thing. Your y values are increasing without bound. So infinity is the preferred answer, but DNE is also acceptable. But infinity is better. You're telling me why. Now, what do you think can be said about the general limit here? Yeah, you could say it does not exist. But here's the thing. Because it's actually doing the same thing on both sides. We know it doesn't exist, but because it's going up on both sides, that's uniform behavior, you can actually say that the general limit is infinity. Now, when you tell me that the general limit is infinity, you're telling me that the limit does not exist, first and foremost, because it goes up now on both sides. When you put positive infinity as a general limit, you're telling me it's going up without bound on both sides. So that's the preferred answer. Okay? So that's the definition of a vertical asymptote. If you ever approach a specific value of x, like -1 or 5 or any other specific x value, if your y values are going to infinity or negative infinity on either side, it's because the vertical asymptote forces them up or down to infinity. All right, what would be the answer to the next one? What would be the limit as x goes to +2 from the left? Negative infinity. It's going down, down, down. So negative infinity is the preferred answer, but again, on a free response, DNE also works. Negative infinity, though, would be the multiple choice answer. So when you tell me that the limit from the left is negative infinity, you're saying first again, the limit doesn't exist, and number two, because the y values are decreasing without bound. What would be the limit from the right of +2? Positive infinity. Yep. Again, positive infinity is the preferred answer, or DNE on a free response. Now, what do you think we have to say for the general limit? You have to say DNE. Good. You can't say plus or minus infinity, because you have to report one answer. And because it's not going up on both sides or down on both sides, it's one of each, you have to say DNE. Okay? You have to say DNE. Now, in each of these cases, what is the function value at -1 or the function value at 2? Let's throw that in there. What is f of -1? Well, remember, for the function value now, we're not looking at the roads. We're looking up and down at -1, and we're looking for a piece of the graph. Does the graph exist here at -1 at all? Nope. So the function value is DNE, does not exist. Same thing down here. F of 2 is also DNE. There is no function value. So are the limits and the function values related in general? Is the limit related to a function value? Yes, only because they're both y values. But do they have really anything to do with each other? No, they can exist independently. As we already have seen now, we have all these wonderful types of discontinuities where the limits and the function values could be the same. In the rare case that both limits and the function value exist, and they're the same y value, then the function's continuous there. But if any of the limits or function values fail to exist, or if any two of them don't equal each other, the function is not continuous there. So the limit, when you compare it to the function value, becomes a very important thing, a piece of criteria that we use to determine continuity. Okay, last problem here, example 5. It says, sketch the graph of -4 over x plus 2 using your knowledge of transformations, and then answer the following questions. All right, what's the parent function here? Anyone recognize it? 1 over x, good. The parent function is 1 over x, so if we remember what that looks like, it has a vertical asymptote and a horizontal asymptote on the y and x axis, and it looks like that. If you want to put this into standard transformation form, you would pull the -4 out of the numerator and leave it as 1 over x plus 2. So let's talk about the sequence of transformations. If you multiply any function out front by a negative, what does that do to the function? Like x squared versus negative x squared, same thing. What does a negative in front of a function do to the y values? Well, in general, it's a reflection across the x-axis, right? Because these are your y values, they're now the opposite. So a +4 is now a -4. A -3 is now a +3. So they're switching across the x-axis. So this is an x-axis reflection. That's going to make this graph look like this now. If you reflect it across the x-axis, it's going to live in quadrants 2 and 3. What does multiplying a function by 4 do? Vertically stretches it by a factor of 4. That just makes the graph steeper. You don't even really have to show that. The important thing, though, is the x plus 2. That picks up the graph and moves it left 2 units. So the vertical asymptote is at -2, which we could also tell by analyzing the domain. So this function looks like this. Here's -2, and there's the vertical asymptote. Here's the horizontal asymptote. And now, since we reflected across the x-axis, the graph lives here and here. And once you have the graph, now you can answer these questions. What's the limit from the left of -2? The preferred answer. Hop on the graph to the left of -2 and you're going positive infinity, or DNE. What is the limit from the right of -2? Negative infinity. You're going down on the right-hand side. What is the general limit? DNE. Good, because those are not the same type of infinity, so we can't generalize it. And what is f of -2? DNE. Good. Is the function continuous at x equals 2? Why or why not? Yeah, no. F has a vertical asymptote at x equals 2. Okay, now what we're going to do after this test is we're going to get back here. This is all we're going to be testing over up through this for Thursday. When we get back from the test next week, we're going to actually define what it really means to be continuous at a point. And it's going to relate to the limit and the function value. Right now, you could just say, no, there's a vertical asymptote there. Okay, cool. So tomorrow on your quiz, your group quiz, you'll get to work together with other people. You're going to have a graph, and you're going to be looking at limits from the graph. Okay? So you might want to check out your worksheet. It's not going to be due on Thursday for the test, but there's some problems on there that involve this type of stuff, and you want to use the worksheet to practice those types of problems. All right, have a fantastic rest of the day.